Okay, so we are going to work on the shunts. I'm gonna go ahead and share my screen. Welcome, everybody. Um, Professor P, let's go ahead and talk about calculations. This is for your hemodynamic part on your CBT. Oh my goodness, I just noticed I added an extra numbers in there. It's 2330. Okay, so when we have talked about cardiac output. Cardiac output is going to be the amount of blood pumped by the heart per minute. This is a general cardiac output. We're not so expecting there's any shunt. This is a standard cardiac output um, test or diagnostic that we are doing when we do right heart. Now, when we suspect that there is a shunt, we are also going to determine, we're going to split that full cardiac output into two cardiac outputs. So we need to investigate each one of them separately so we can find where the problem is. So we do have, in this case, we do have regular cardiac output or cardiac output as we know it, and then we have systemic cardiac output, which is the systemic cardiac output is going to be, because I forgot I'm on the other screen. Systemic cardiac output is the volume of blood between the AO and the RA that is in your system, in your body. That's why I gave you this image of a full body. So when the blood leaves, and actually here instead of RA, should we actually say mixed venous return? So we are going from the AO when the blood leaves the heart from the aorta to the body, and then right before the blood comes back to the heart through SVC and IVC. And you're gonna see why I did RA specifically for our samples. Okay, but in the absence of SVC and IVC, which will be the mixed venous return, where we are going to use the Flam's equation, right? 3 SVCs plus one IVC divided by 4. That will be your mix. So we want to know the oxygen percentage from SVC, which is going to be a little bit lower than IVC as we spoke in class, right? Because the brain uses more oxygen. So naturally, the SVC is going to come a little bit lower. And then the IVC is going to come. And they're both going to drop the blood into the right atrium. So in the absence of SVC and IVC, we're going to use RA. That's why I decided to go for RA here, just so because it makes more sense to our samples. But if you do have, say on your RCIS, you do have SVC and IVC, then you apply SVC and IVC for your mixed venous return. All right, and then we also have the pulmonary cardiac output. So this is the amount of blood that your lungs process through the pulmonary vein and the pulmonary artery, going to the lungs and coming back. Okay, so to make a little bit more sense, we have three. We have to find for three cardiac outputs: general cardiac output, systemic cardiac output, what goes outside of the body, and then pulmonary cardiac output is what goes outside of the body, but this time to the lungs. So what the lungs process. Okay. And then we're going to take a look at the next slide here. On this slide, for all three, we're going to use cardiac output formula because it is cardiac output. We are just applying it to different places. Remember to look for that Q. What am I doing? Q means flow. So on this particular Q, this is going to be systemic flow, and this is going to be pulmonary flow. Q equals flow. Okay, so when we look at the formulas, our regular cardiac output is going to be cardiac output, VO2 or assumed VO2 minus arterial venous difference times 10. If we look at all three of them, look at the formula. CO divided it's going to be the assumed divided by AVO2, difference times 10. And if we go to the QP, is going to be VO2 minus AV, O2 difference times 10. All three are the same. I just added QS so you can identify which one is which, so you know which saturations to use, which oxygenation information to use. Because for the systemic, I'm not going to use anything inside of the heart except for RA if I don't have any information, but I'm going to get the blood samples outside of the heart, AO and mixed venous. And on the QP formula, I'm going to use PA and PV. Okay. So I'm going to erase all this. Cardiac output formula, that's what I'm going to do. Nothing else. Okay, so this is the formula for shunts. The formula for shunts, I want to know the ratio of blood of both sides of the heart. In a perfect system, the cardiac output from the right side should match the cardiac output of the left side. So both systems, even though the right side of the heart is low pressure system, it processes the same amount of blood that goes through the left ventricle out to the body, right? It only makes sense. It comes in and goes out, comes in and goes out, right? So I want to know if there isn't a difference between what comes in and what goes out. This is how am I going to find the shunt. In the ideal world, I want the ratio to be 1, because that's going to mean that there is actually no shunt, 1-to-1. And then we're going to talk about what happens when our ratio is not 1. Okay, so in this formula, like it says here, we're going to compare the amount of blood pumped into the pulmonary circulation to the amount of blood being pumped into the systemic circulation. We compare the two systems. We're going to use the cardiac output formula to resolve for blood flow. So let's take a look what QS looks like. We already saw it, but let's look at them together. QS is the formula for QS is cardiac output. We are just going to plug different information because we are looking at the systemic, which is AO, and mixed venous or RA. For QS, I'm going to substitute or plug AO O2 saturation minus mixed venous O2 saturation times 10. For QP, I'm going to use PV and PA. And remember, minus symbol means difference. So I don't know how you're going to see it on your RCIS or any other material. It could be a minus, it could be a difference, it could be AV diff instead of AO2 minus MVO2 diff saturation. However it's written, the concept is going to be arterial and venous samples, or oxygenated and deoxygenated samples, to better say it, because it doesn't apply for all 3 samples. So the high oxygenation minus the low oxygenation on the systems. Okay. Now, a new formula comes into play here. When we talk about mixed venous return, that means the blood that comes back to the heart right before it gets into the right atrium, SVC and IVC. For that, we need to use the Flamm's equation, which is going to be 3 SVCs plus 1 IVC divided by 4. I think that formula got here cut, but we're getting an average, right? So we have 4 pieces of information, we divide by 4. And that's the only extra step that we are going to do if we get SVC and IVC information. If we do not get that information, we are going to substitute the mixed venous for RA, because ultimately the RA is where SVC and IVC mix. The problem will be, it'll be a little complicated to determine if there's a shunt, the atrial shunt or atrial septal defect, if we don't get SVC and IVC, because the RA might be compromised due to a shunt, right? Or the information, not compromise itself, but the information that we get. Okay, we already said Q is for flow. For PV, we're going to get the pulmonary venous oxygenation and the pulmonary arterial oxygen. As we know, the PV is higher oxygen than the PA. Okay, let's go ahead and remove all this. Let's go on to the next slide, which is where we are going to practice. So you do have this information on your calculation sheet that I gave you. So I just plugged all the information here. Just to make a correction, on number 8 should say PVO2 because it says CCO2. Let's go ahead and substitute for PVO2. Other than that, everything is the same. So when I see a problem, think of the chicken parm recipe. Do I have the ingredients to get chicken parm? So my ultimate goal is to get chicken parm, right? So what is the ultimate goal when I see a problem or when I'm going to resolve or when I'm being tested, right? Okay, so it says here that I need to resolve for all this. Okay, so I'm going to look one at a time. For BSA, do I have information? Yes, I have height and weight where I can get BSA. Perfect. VO2. How do I get VO2? Well, I get BSA by times 125. So I do have the information. Yay. Now I have AVDO difference. We are resolving for Fick cardiac output, right? So don't get confused on the shunt yet. We need to see the regular cardiac output is systemic and then pulmonary. So right now I'm going to resolve for general cardiac output. Now, do I have the AVD saturations or oxygenation to resolve for Fick? I'm going to go to my image, to my graphics that I have on my packet, and I'm going to look at sample A. And then what information do I need for AVDO2? I need arterial, I need as AO, and I need PA. Do I go to my sample? Do I have AO and PA? I do. So that means I can also resolve for AVDO2. Great. Now, can I resolve for Fick? Yes, I can because I already have VO2 and AV difference. So I do have all the information. So that's how you should work on the problems, right? One step at a time and work through towards the final answer, which in this case is going to be shunt. Okay. Going a little bit lower on this information here, I have CaO2, CvO2, PaO2, and PvO2. Okay, so if I see what I'm looking for is the shunt, I know I have to resolve for QS and QP. So do I have information? That's the first thing I'm going to do. Do I have information for for QP and QS? Okay. So for QS, what information do I need? I said it's the system. Okay. So I'm going to need for the system, I'm going to need samples of AO and the mixed venous return. I'm going to go to my graphic on sample A. I do have AO, which is 91%. And then I don't have information for mixed venous return. Like, okay, what do I do now? Well, chicken parm. In absence of breading, go ahead and get crackers, go ahead and toast the bread, or substitute the breading for another product. In this case, I don't have SBC and IBC, but I know they mix in the RA. So, okay, that's a possibility. I do have the information for systemic, right, to get QS. I have AO and I have RA. Great. Now, what information do I need for QP? I need PV and PA. Okay, so I'm going to go to my graph again. I do have PA. I see this 76%, but then I don't have a PB. So what PB, chicken parm, go to your ingredients. Do I have the information for PB? Well, I do not. On my sample, there's no information on the PB, but I know the pulmonary veins drop the blood to the left atrium. And I do have a sample for the left atrium. Okay, so I can substitute LA for PV. Perfect. So that means I do have all the pieces of information to resolve these problems. Okay, so I'm going to start working on my samples here. The first thing that I'm going to do, you have to remember for your exam, if BSA is going to be given, what I want you to practice rather is convert it to metric system, the 5.9 and the 195 pounds. So go ahead and practice that, do it on your own. And then I'm going to go ahead and give you a BSA. For this samples, I want you to go and get on the online BSA online calculator and use the Moseller formula. So in this case, BSA is 2.08 square meters. Okay, so I'm going to go ahead and resolve or put here 2.08 square meters. Good. My next problem, number 2, is VO2. So VO2, to resolve for VO2, my formula is 125 times BSA. And I already have BSA, so I can go ahead and resolve for VO2, which is going to be 125 times, I already have 2.08. So my VO2 is going to be VO2 equals, I keep doing the colon. Okay, so it's 260. Okay, so I'm going to come back here at the bottom and I'm going to write 260. Okay, my next is the difference, ABDO difference, because I'm calculating prior to Fick. Okay, so what I'm going to do here, I know I have AO and I know I have PA. So all I have to do for AV difference O2, this is my formula here. Oh, I see why it's called because I have it in capital letters. So I'm going to go ahead and plug my numbers. So I have 0.91. And when it says the ABDO2 saturation difference, I have to multiply, remember, is the same cardiac output formula times, and going to my patient information, my hemoglobin is 15. And it says a difference. So then I go, I forgot what is the PA, is 76. So 0.76, because it's percentage, times, again, 1.36 times 15, which is my hemoglobin. So let me go ahead and open this a little bit. There you go. So I can resolve for that. So I'm going to go ahead and grab my calculator. And I'd like to go ahead and do and type again my formula. So just, I don't get lost. If there's a mistake along, I can come back and trace it. Otherwise, I'm going to lose it. I will not be able to recognize it as easily. So I'm going to do 0.91 times 1.36 times 15, which is my hemoglobin. And my result here is 18.56. And then I'm going to resolve the second part, which is going to be 0.76 times 1.36 times 15, which is my hemoglobin. And this is 15.50 or 0.5, because we're gonna work with 2 decimals. Okay, so ADO2, my result here is going to be 18.56 minus 15.5. My result is 3.06. Okay, so I'm going to go ahead and plug it over here, 3.06. Perfect. Now, can I get Fick? I can get Fick because I have VO2 and I have ABDO2. Perfect. I'm going to go ahead and do cardiac output. My formula is VO2 divided by AV difference O2 times 10. All I have to do is go to go ahead and unplug. Cardiac output equals 260 divided by my difference is 3.06 multiplied by 10. And I like to do it like that, one step at a time. So when I do it, again, I can recognize if there's anything wrong. So here will be 30.6. I resolve one more time, cardiac output equals, so I'm going to go ahead and use the calculator, 260 divided by 30.6. That's going to be 8.49. You might say, okay, it's 0.4967, just leave it at 49. And what are my units for cardiac output? Liters per minute. Okay, so I'm going to come back here and write 8.49 liters per minute. Now, I already know I can start working and using my critical thinking, right? There's something wrong here. What is my normal cardiac output? Like normal cardiac output is between 4 and 6. Some information is 7 or even 8, but look at my patient, my height and weight. This is a normal sized person. This is probably a man. I don't know. I'm just, I don't know. I have to determine through height and weight, is it 8.49 normal for a person this size? If it was somebody who's really, really big, like a basketball player or a football player, maybe. But I can already see like, maybe. All right. Let's go on to the next part. Remember, I'm still using cardiac output formula. So I'm going to go ahead and resolve each one of them separately so it makes more sense. Okay. So let's resolve for QS first. For QS, which is, I'm going to use, let me just remove this one. So I'm going to work on my Q. I know these two are for QS and these two are for QP, right? So I'm going to go ahead and resolve for QS first. So QS is my system. That means I'm going to use VO2 because it is my cardiac output. And now what information do I need for my system? Well, I'm going to need AO, right? Minus, I already know there is no mixed venous, but I do have an RA difference. Let me put O2 difference. O2 difference. And then times 10. And that's all I have to do. For QS, I'm going to do equal VO2, I already know is 260 because I already resolved for that. Now I'm going to go ahead and substitute in the whole entire formula, right? So it's going to be 0.91. I think it was her formula or saturation for AO, 0.91 times 1.36 because it's my constant and times hemoglobin, right? Minus, now I'm going to go on to my other value, which is my venous value. My RA is, I believe, is 78. So it's 78%. So it's going to be 0.78 times 1.36 times 15, which is my hemoglobin. And then all that times 10. I'm going to go ahead and extend my formula here so everything looks clean and straight. All I have to do is just resolve for this. 260 divided by, and I'm going to go ahead and do my numbers. So I'm going to go ahead 0.91 times 1.36 times 15, and it's going to be 18.56, which will be CaO2. And then I'm going to do minus CbO2, 0.78 times 1.36 times 15, 15.91. 15.91. I'm just doing a parenthesis because all that has to be multiplied by 10. So I'm going to go ahead and resolve again one more time, even if it looks like pretty long, I'd rather have that. So now I'm going to do 18.56 minus, oh, I said 15, 18.56 minus 15.91. This result is 2.91. 2.65 multiplied by 10. QS equals 260 divided 20 by 26.5. Once I multiply, so when I do this math, is 260 divided by 26.5. My cardiac output here, or my QS cardiac output is going to be equals 9.81 liters per minute, because I'm calculating systemic cardiac output. Flow cardiac output, right? Okay. So given these values, I can go ahead and let me erase this so we can make it a little clear. I can get that little step. Okay. All right, for CaO2, I'm going to go ahead and get my number here, which was my arterial, which is 18.56. On the next one, it'll be 15.5. Resolve already for those two. And I'm going to go ahead and now resolve for QP. And I'm going to do the exactly same thing. I'm going to do VO2 divided by, so what is my oxygenated blood here? So it's going to be my PV minus PaO2 difference times 10. QP equals 260 divided. Go ahead and plug all of your numbers. When I come in, I go back and look at my diagram again. So I have for PV, we already have determined that if I don't have PV, I can use LA, because at the end of the day is the blood that comes straight from the lungs through the PV. So I have 98. So it's going to be it's 98%, right? So it's 0.98 times, again, 1.36 times 15, close the parentheses, minus, because we're looking at a difference, and then your PA is 76.76 times 1.36 times 15, and this will be all that times 10. And maybe I should have done a bracket over there, but let me resolve again here. QP is going to be equal to 260 divided by, so I'm going to go ahead and use my calculator again, plug in the numbers. So it's going to be 0.98 times 1.36 times 15. So my first number is going to be 1999, which I had already calculated on my other oh no, I have a calculator for my other formula. So 1999, because I thought it was 91, but I think I made a mistake here. Is because oh no, this is PV. 1999 minus, oh, let me do a formula bracket. So result for PA, which is 0.76 times 1.36 times 15, which is my hemoglobin. So it's going to be 15.5. And all this, I'm going to multiply by 10. So QP, again, 260 divided. So go ahead and remove 1999, subtract 1999, and then 50.5 is going to be 4.49 times 10. One more time, QP equals 260 divided by 44.9. And then lastly, I finally made it to my result. So it's going to be 260 divided by 44.6. And this is going to be 5.82 liters per minute on my pulmonary flow. Okay, so I have all the information. Go ahead and plug here if you want. This is going to be 1999, and this one is going to be 15.5. Okay, so for my shunt, I want to know, remember, so it's QP over QS ratio. That's what I want to know. So then I'm going to go ahead and substitute. So for QP, I have 5.82. And I want to know what is the ratio to the QS, which is 9.81. Now, looking at this result, the QS and the QP, I know there's a problem. Because remember, the right side of the heart should pump the same amount of blood than the left side of the heart pumps. So what comes in goes out from the heart. So look at this number. So I can start looking at things and be suspicious of a shunt. Now I'm going to go ahead and do the ratio, which is going to be 5.8182 divided by 9.81. So my ratio here is going to be 0.59. Now, if it's 0.58, 0.57, somewhere around it is going to be okay. Because it depends on if you calculate it with 2 decimals, with 1 decimal, 1 decimal could be a difference. But when we have this information, that is certain, I am certain that I do have a shunt. My rule says, if the ratio, well, let me take off the capital letters. If ratio is less than 1, that means it's a right to left shunt. If the ratio is larger than 1, then you have a left to right shunt. So what can we determine on this shunt that we have here? Well, we can determine that this is a right to left shunt because it's less than 1. So here you are going to write 0.59, and it's going to be a right to left shunt. That will be your answer there. Yes. So what is happening here, and let me erase this. No, I don't want to clear all the drawings because then everything goes out. Just this and probably this. Okay. So let me go ahead and draw a beautiful heart with my little manitos. Okay. So say it's a heart, right? With a lot of imagination. This is your septum. And we have the right atrium, left atrium, right ventricle, left ventricle, right? So it says that it's a right to left shunt, and I can see it clearly because I do have way more blood on the system than when I have in the lungs. So if the left side of the heart is pushing away, let me remove this one because maybe I can switch color. That will make it a little bit difference. If the left side is pushing away, through the aorta, more blood than what the right ventricle is pushing to the lungs, that means there is an excess of blood on the left side. So I have more blood here. But where is this blood coming from? Well, it is coming from the right side to the left side. And that's how it increases this volume. Now, I want you to take a look at your diagram A and look at the saturations. So we have 78 for the right atrium, 78, and then we have 78. Oh, look at this. And then over here we have 98. And then right here we have 92. So just by looking at it, I need to know what normal is to identify what normal is not, right? So it's 78. Let's take a look at the right side. 78, good for the RA. Pretty much, yes, it's a little high, right? Typically it's a 75, but it's within the range. So the increase is not that much, right? Now, 78, and as I know the flow, right? Right atrium, right ventricle, 78, 78. Well, it looks good. Now, let me look at the left side. So what is my normal oxygenation on the left atrium with the blood coming back from the lungs? 98 looks pretty good, right? It looks good. Now let's take a look at this one. This one does not look good at all. So what is happening in the left ventricle? So how come it went from 98 to 92? Well, it got contaminated with the oxygenated blood, which tells me that my defect is a ventricular septal defect. Because here, if it was a natural septal defect, the oxygenation will differ on the atrial. But since it's differing in the ventricle here, and my shunt is from right to left, that means the right ventricle is pushing the blood over to the left ventricle, contaminating and bringing the oxygenation down. So the problem here is this 92 goes out to the body as 92 instead of a 99 or 98 in a healthy person. So the brain is missing oxygen, the muscles, the organs, everywhere is missing oxygen with this number. Okay. Well, I hope that makes sense. Your other two samples, 4 and 5, are exactly the same. Use the same formulas. See if you can substitute. Use the chicken parm if needed. This is when we start, using our critical thinking. What can I use instead of, or where's this coming from? And getting to know why the right side is contaminating the left side. See if all the shunts, you have to determine on the next two, if there's a shunt. Second, if there's a shunt, which way is it going, right to left or left to right? And the way to know it is with your ratio. Okay. Well, that's all I have for you, and we'll see you soon.